example 12.8. This is going to walk us through finding normal vectors to level curves, which are the gradients of higher dimensional functions. It's going to walk us through tangent planes. It's a pretty good problem. Let's get started. Let's consider the function x times y times z is equal to -4. I want to give a function for which the given equation is a specific level surface. So I'm going to choose my function of x, y, and z to be just x times y times z. So this function, the function that I'm given, is a specific level curve of this function, right? It's when x, y, z gives me a -4. All right, next question. Give the family of normal vectors to the level curves. So this function is going to have a bunch of level curves. In fact, here's one of them. The normal vectors to those level curves are given to me by the gradient of this higher dimensional function. So the gradient of f is given to me by yz times xz times xy. All right, so this is going to be a normal vector to any level curve that I want, right? Because I didn't use the fact that I'm looking at the specific level curve of -4. This is going to be normal vectors to any level curve to this function right there. All right, next part. Give the normal vector to the equation at a specific point. So this is me specifying, hey, I'm looking at this level curve. This, hopefully, is a point on that level curve, and I want to give a normal vector there. So let's just double check. If x is 2, y is -1, and z is 2, yeah, that satisfies this specific level curve. X times y times z is equal to -4. So this point is on that equation. So the normal curve is going to be my function, or sorry, my gradient vector evaluated at 2, -1, and 2. This is going to give us a -2, 4, and a -2. Okay, next part. Give the equation of the tangent plane at this point. Well, I have the normal vector, and that is the normal vector to this specific level curve, or that equation at that point, right? And we know how planes look like. It's x component of normal vector times x minus the x point, and the x point is 2, plus the y component of the normal vector times y minus the y component of the point, -1, plus the z component of the normal vector times z minus the z coordinate of the point. Okay, so that's the equation of the plane. You can clean this up a little bit, move your constants to the other side. You end up at -2x plus 4y minus 2z is equal to -12. And then finally, give the equation of the line that passes through this point, 2, -1, 2, and is parallel to the normal vector. So the equation of a line, let's use the vector form. It's the initial point plus a parameter t that moves along your velocity vector, or the vector that points you in the right direction. So obviously a point on the line would be this point, right? I'm looking for a line that passes through that point. So 2, -1, and 2. And then the direction of my travel, I need to be parallel to the normal vector, i.e. I need to be traveling in that direction. So this is the normal vector. Cool. So finding tangent planes, you need a point, which are going to be often given. You need a direction vector, or a normal vector. The normal vector is found by interpreting your specific function as a specific level curve of a higher dimensional function, using that higher dimensional function, finding its gradient, which is going to give you the normal vector that you're looking for.